Where do you even begin? It's not like you know which chapter to pull from because every chapter is fair game. And if you're in Orgo 2, every chapter in Orgo 1 and Orgo 2 are fair game. So what a lot of students do is panic. We are going to take that away. What a lot of students do when they're done panicking is anything along the lines of starting with the reactant, thinking about the thing backwards. So starting with the product, I don't know why I did that. Or what some students do is they just write everything. The problem with this approach is unless you know exactly what the reaction is and where you're going, this is no good. What if you start with a reactant, get halfway there and get stuck? You start with a product, work halfway back and get stuck. What if you write everything out and realize, yeah, I don't actually know where I was going with it? Or worse, your mind goes completely blank. The reason it gets trickier now is up to now, it's been reactant A goes to product B. Or if your professor is being a little bit more devious, it would be reactant A goes to product C. And you would have to come up with some intermediates for B, maybe C, maybe D. And now, let me see thumbs up in the comments if I am not exaggerating, if your professor does this. Here is molecule A. And somehow, some way, with zero exaggeration, come up with product Z. And that many steps in between. That is where it gets confusing. This is where many students panic, and this is what I'm going to show you how to avoid today. The first thing is we cannot go from A to Z. You're thinking A, you're trying to picture everything till Z. It's too overwhelming. It's too many steps, and it's too much to try to predict before you know exactly where you're going. So one tip that I recommend, one way to break this down, is instead of having to do so many steps at a time, what if you can take molecule A and know at least that you have to go to B? That's one step that you can think of. And if you need product Z, well, maybe I can come up with the steps from Y to Z, just one step. And that's an easier reaction. And what if I take this another step? And I say that I know how to go from B to C. I know how to go from X to Y. And now I have an even smaller reaction to solve. So yeah, the idea is retrosynthesis, but I like to do a mix of forward and back, meaning a little bit of synthesis forward, a little bit of retrosynthesis backwards. But I'm never going from A to Z. That is too much to follow at once. I'd rather break it down into smaller steps that I can then just have clues that tell me this is the next piece, this is where I want to go. But even if you were able to get to this point, if your mind blanks out, then none of this will help. Let me know in the comments if that is what happens to you. You see the question, your mind goes blank, and then no matter how well you studied, you can't get past that because there's nothing actually coming to you. And it's very, very hard to come up with examples. So if that's the case, what I like to do here is busy work, simply for the purpose of I need something to jumpstart my brain. And once you get in the flow, have you ever noticed that when your mind goes blank and you panic, and then whatever happens when you get in the zone, when your brain finally turns on, it's just very easy to keep going, but you kind of lost half an hour in the process. But if we can jumpstart your brain, and Mars, if we can get you there faster, if we can get this to not happen to you, Ms. Jess, then you'll have a lot more time for the things that matter. And the busy work is the easier thing to memorize, the easier thing that you can ask yourself, step one, step two, let me answer it. Let me come up with such a simple question that my brain automatically knows what to do next. And the busy work is to ask the following questions, which my Orgo 2 students, if you have been in any workshops with me where I've done reactions, you've seen this already. Question number 1, what's the same? And question number 2 is what's different? This is so easy. Do you think that this is easier to ask yourself when your brain is blank than asking, how do I get to that molecule? How do I solve this synthesis? And what specifically am I looking for in terms of what is the same and what is different? I'm looking for the number of carbon atoms. Did my chain grow or shrink, or did I simply have to change things on the chain? What are the functional groups or the substituents or the molecule pieces that I have to change? Did I start with a halogen and then put an alcohol or an alkene? Or what did I do to the group that I had on there? And the third thing I'm looking for is the POR, or the position of reactivity. And what this is simply where on the molecules is happening. If I had something on carbon 2 and now it moved to carbon 3, that position where I'm reacting, the position of reactivity has changed. And I want to know how I'm going to make that change happen. So by asking yourself what is the same and what is different, and then trying to think of just how to attack that difference, you will find that your brain just lets go of the panic of how do I solve this problem, and lets you address that easy question of what it is that I have to do. So let's demonstrate with a problem that is hopefully not difficult at all, so you can see what to do and how this works. So let me know in the comments if you think this is easy, medium, or hard. And then we'll walk through not so much the question for the sake of the question, but rather build up the ability to solve this kind of problem. You see something like this on your exam. What is your first thought? How do you approach something like this? Yes, you are very, very welcome. Thank you for that. Well, we want to ask the two important questions. First, if you are just joining or if you're watching the recording, welcome. For a copy of tonight's session notes, just copy live notes and I'll email you the PDF of everything you see me draw tonight. I also have a brand new organic chemistry pre-finals assessment, which I'll discuss more at the end. So hold on to that thought and let's work this out right here. With question number 1, what is the same? When looking at what is the same, remember number of carbons, then the groups and where the groups are located. I like to number everything so I can clearly match reactant to product. 1, 2, 3. And that would then be 1, 2, and 3. So what is the same in this case is the number of carbon atoms. But question 2, what is different? Well, I turned a bromine on carbon 1 into a carbonyl. And so what I have to figure out here is how do I turn bromine, which is a good leaving group, into a carbonyl, specifically an aldehyde, which is an oxidized functional group. Now that I have the questions, now I can start thinking about how to bring about just that transformation and make that happen. So I see medium, excellent. So we're looking at the functional groups, yes. Bromine to alcohol and an oxidation. Alicia, I challenge you that even though this question feels very easy and straightforward, I want you to pretend it's not that easy so that you can get comfortable with the process. And then when the question is really tricky or difficult, you know how to use the same approach because you've practiced it on the easy questions. Did the number of carbons stay the same? Yes, and it is just the groups themselves that changed. And so again, pretending that we don't know how to solve it, because I don't know how to go from a bromine to an aldehyde, I have to think of a different question. Remember how I showed you that if I don't know how to go from, where did I have it? From A to Z, I can go from A to B, from Y to Z. So take it one step forward, one step back, and kind of inch closer and closer to something that makes sense. So let's take a look at the product. If I don't know how to go from a bromine to an aldehyde, is there something else that I consider? What if I completely disregard the fact that I'm starting with a bromine and simply ask, what reaction do I know that can give me an aldehyde from anything else? Well, what can give me an aldehyde? The easiest one is oxidation. If I do an oxidation reaction, then one step prior to the aldehyde, I will have an alcohol. And the alcohol will be on the same carbon. So the only thing that changes from this reactant to the product is that I oxidize it to an aldehyde. So now I have a simpler question to ask. I ask myself, is there a reaction that I know that will take me from bromine to the alcohol? Because this is no longer my problem. Now the problem is just going from here to here. I like to do all my intermediates first and then go back and fill in the reagents, because intermediates are a little bit harder to get. Reagents is kind of straight up memorization. Also, I found that when professors will give you partial credit, they will take off fewer points if you mess up the reagents, especially, and here's the trick, if you don't remember the reagents, make something up that has the thing in it. So let's say I forgot how to go from a bromine to an alcohol. I'll just put OH2. Totally made it up, but it kind of sounds like I maybe memorized it wrong, and I will get a little bit of credit for it. So why not? Welcome, Ishan. It is good to see you. Better late than never. And of course, you can catch up on the recording after. So the question then is, do I know of a reaction that will turn a bromine on carbon 1 into an alcohol on carbon 1? And the answer is absolutely yes. I will note the different reactions. That way, if you know that you need to review for your final, but you're not sure which chapter, this will help you out. So going from the bromine to the alcohol, this is an SN2 reaction. Going from the alcohol to the aldehyde is an oxidation reaction. This comes up in a couple of different chapters, so see where your book has it. And then let's fill it in. From bromine to alcohol is an SN2 reaction. SN2, substitution, nucleophilic. I never use SN1 or E1 in synthesis unless I have to, because the SN2 and E2 is going to give me fewer side products. To get the reagent for an SN1, all you do is take the group that came on there, the nucleophile, give it a negative charge by giving it a counter ion. So there we go, NaOH. To make sure that it goes SN2 rather than E2, I want to have a polar aprotic solvent like DMSO. That tends to be my go-to in synthesis. And then for oxidation, because I'm stopping at the aldehyde, I don't want it to go all the way to the carboxylic acid. I need to use a weaker inhibited oxidizing reagent, and PCC, pyridinium chlorochromate, is the one that I will go with. And that's how I get my product. Now, again, this problem is not very difficult, so don't worry about this was too easy. Instead, my question to you is, seeing this concept demonstrated by breaking it down, do you think that will help you be less stressed or less overwhelmed on your final exam than just trying to brute force it going forward or backwards and then just getting overwhelmed and stuck? And a question. We can do SN2 because the bromine is primary and unhindered. Yes, that is absolutely correct. SN2 can only happen if there is access, meaning it's not too sterically hindered. And the easiest is a methyl, then primary, then secondary, and you cannot have SN2 for tertiary. Very good question. So I'm glad we clarified that. I barely know what's going on in my lectures, so I think this breakdown helps a lot. Mira, unfortunately, a lot of professors, they don't like to teach. I think that's the problem. It's not that they don't know how, it's that they just don't care to, so they kind of show up, phone it in, I think is the expression. But I love this, so I'm so happy that you're giving me your time so that we can work on this together. And hopefully, regardless of what's going on in class, you understand it well enough to ace this material. And at the end of the day, that's all that counts. Now, if you are in Orgo 1 and you have not yet learned oxidation, there is another way that you can solve this problem. I'm going to show it to you quickly because I want you to know that you are not locked into, let me try it the other way. You are not locked into just one approach. The more reactions you learn, the more pathways you'll find for coming up with any kind of product. And sometimes if you go one way and you get stuck, you can do a completely different way. So if you are in Organic Chemistry 1, you have not learned oxidation, and you do still need to come up with that carbonyl, the other reaction that you could have done is turn it into an enol and then do keto-enol tautomerization. So the enol would look something like this with an OH and a carbonyl, which you hopefully recognize would have come from an alkyne. like this. And then, so let me just draw this right here. We'll fill in the intermediates first and then go from there. Now we ask a different question. If I didn't know how to go from here to here, do I know of a reaction that will get me from bromine as my leaving group to an alkyne? And the answer is no, I don't. Because I don't know how to do that, once again, I'm not going to look at this and just look at my alkyne. Ask myself, is there another route that I can go? If I disregard bromine as the leaving group, the question that I want to ask, do I know how to make an alkyne from anything else? How can I make an alkyne? Well, I know that I can make an alkyne with double elimination. Kind of squeeze myself into the corner here. I know how to make an alkyne with double elimination. So let's do here. We'll use bromine because I want to show you a trick here. If I have two bromine atoms next to each other, I can double eliminate. So then I have a new problem. Do I know how to go from a molecule with one bromine to a molecule with a second bromine? And the answer is no. No, I actually don't know how to do that. I don't know how to add a bromine to the next position. So we have to pretend that these are different bromines that have nothing to do with my starting molecule, and therefore ask the question, what molecule can I use that will give me two bromines on it? I know that I can react an alkene to give me two bromines, and then I keep coming back to my starting molecule. So let me show you what I did. I didn't know how to do that, so I went here. I didn't know how to do that, so I went here. I didn't know how to do that, so I kept ignoring the starting molecule, going one step back, and now I ask myself the same question. Do I know of a reaction that will give me an alkene from bromine? And the answer is absolutely yes. So let's go ahead and fill it in. Let's keep this consistent. The first reaction is an elimination. I'm going to go with E2, even though E1 would work as well. I'm just keeping it in purple, isn't I? So I do an E2 reaction. That will give me the alkene. Then I do an alkene reaction, specifically an alkene addition reaction to give me the dihalide. The alkyne reaction is going to give me the alkyne. And this is also in the alkyne chapter to add to the alkyne. So let's fill in the reagents. For an E2, I like to use any small base and heat. So we'll use NaOH in this case, its own conjugate, water and heat. Once I have the alkene, if I want a dihalide, I just react with a dihalide, Br2. You typically don't need to show the reagent, but you can show anything inert like CCl4. To go from the bromine, the two bromines to the alkyne, I need a very strong base. In this case, we'll use NaNH2. Let me make sure that looks like what it is. NaNH2 in NH3 liquid, but I can't stop here because that will also deprotonate and give me the deprotonated alkyne. And so I have to do a step 2, and that is add water. That will give it back the hydrogen. If I'm doing a chain elongation, then by all means, I want to deprotonate, but over here I don't. So I add the hydrogen back. The next step to get the enol, because I'm putting the alcohol on the less substituted carbon, I'm going to do a hydroboration, which would be B2. I did not give myself enough room. Let's move this out of the way. Stretch the arrow a bit. There we go. Oh my goodness, I'll just redraw that. I want to make sure everything is clearly legible. Okay, so we have B2H6. You'll also see 9-BBN. BH3 is the one you learn more in the alkene chapter, but same idea. B2H6 in THF, followed by that step 1. Step 2 would be NaOH and H2O2. This right here is an intermediate that is not really isolated, but I do want to show you that it stops, that it goes through the enol intermediate. And then, and this will happen automatically, keto-enol tautomerization. We're already in base, so we don't need to do anything. We'll get the more stable, in this case, it's an aldehyde, but it's the keto form for the keto-enol tautomerization. So let me see hearts in the comments if you're liking this approach so far. Again, we had the same starting molecule, the same product, two very different approaches, because if one option doesn't work, but you know another one, just do the other option. Ishan, I'll talk about that at the end. Organic chemistry is honestly just like a giant puzzle. Yes, and the difficult thing about it is that you have to put the puzzle pieces together. On your final, you have to put everything together in one single question. I mean, look at how many chapters we tackled in this one problem. And so this is the approach I like to use, that I'm not overwhelmed. But how do you study for something like this? Because in the alkene chapter, you study alkene reactions. In the alkyne chapter, you study alkyne reactions. In the EAS chapter, you study aromatic reactions. How do you get to a point where you can just know everything and be able to pull reactions from all the different chapters at once? Here is your challenge. And let me know in the comments, yes, even if you're watching the recording, if you are ready to try this either tonight or tomorrow as soon as possible. Unlike how you've been studying before, I recommend that you study not by chapter, but by functional group. I will show you a very simple map so you understand what I'm talking about, but then I challenge you to come up with your own functional group map so that you can really learn to put all this together. What you want to do is take one simple functional group. So for example, an alcohol. And now think about all the chapters that you learned that covered the alcohol. When did the alcohol come up? So there are two ways that the alcohol came up in the previous chapters. Option one is how to make an alcohol, and option two is what to do with that alcohol. So let's start with how to make an alcohol. I can make it from an alkene. I can make it from an alkyl halide. So that's the alkene chapter, the substitution chapter. I can make it through reduction. So that would be the redox chapter. I can make it by opening an epoxide, the alcohol ether epoxide chapter. So do you see how we just came up with a couple of different ways, but if you practice them all together, now it starts to click. I need an alcohol. These are my options. Have you ever put them together? Like, has your brain ever sorted them and gone, oh, all these chapters can come together and give me that alcohol? But you're not done. Once you have that alcohol, what can you do with the alcohol? You can do oxidation. So for example, you can take that alcohol and turn it into, if it's secondary, a ketone. If it's terminal, an aldehyde, or a carboxylic acid. Now, Orgo 2 students, you don't stop there. You say, oh, carboxylic acid, well, what can I do with a carboxylic acid? Can I turn it into an acid halide? Can I turn it into an anhydride? What about an ester? What about an amide? Just anything else. So now, if I have a synthesis where I need an ester, I can follow the path from alkene to alcohol to carboxylic acid to ester, but I get to study that all in one go. I get to study that all in one, like in one context. So I get used to seeing them together, as opposed to, here's the alkene chapter and the alcohol chapter and this chapter and then that chapter, and never fully combining them all. I'll give you a couple more food for thought so that you can go home and play with this even more. I can turn that alcohol into an ether. I can turn that alcohol back into an alkyl halide, and I did it here primary. You could do it as secondary. I can turn that alcohol back into anything that it came from with the right number of steps. And then you take this one and you do the same thing. You take this one, you do the same thing. This is the kind of exercise that you can just play with and keep going and going and going. And before you know it, you know how to do synthesis, because everything just connects. Let me see mind-blown emojis in the comments if you're with me and if you're excited to try this. Alicia, yep, I love that YouTube immediately posts the recording, because that way you don't miss anything. It's there for you right away. Hey, Sean, I know you're an Orgo 2, so you have so many more reactions. So I challenge you, go all the way back to Orgo 1, trace it to your carboxylic acid. Oh my goodness, he's crying again. This child does not sleep through the night. I don't know what is wrong. Don't worry, my husband's got him, but he's crying. All right, so I see the emojis coming in. Within this, I don't know what you call it, the pattern map. Another thing that is going to be really, really important for your final exam when you're doing all these different reactions in one synthesis is patterns. Because it's one thing to know how to do it. It's another, a faster way to recognize, oh, I see this, it has to be that pattern. I see this, it has to be that pattern. Sometimes the patterns have more than one step, and that just makes it so much easier because you don't have to process all the different steps. You see immediately, that's the reaction I'm going to use. So what you want to do is look for clues that are going to tell you, oh, this is the pattern that I need to work on. So my favorite pattern, and therefore the first one we're going to look at, is the move of the functional group pattern. Because often you're given a molecule and it has something on it, maybe a leaving group, maybe a pi bond or something, but you need to react it in a different part of the molecule. So I'll show you a problem. Let me know in the comments if you think this is easy, medium, or hard, where we have a starting molecule with a bromine sitting right there. And somehow, some way, you have to come up with a synthesis to show me how to put the bromine right there. You see this on your exam, you know that you have to move the functional group. What? Well, first of all, what do you think? Easy, medium, or hard? And how do you even begin? What is the best tips for having a summer break between? So I have a workshop that I did on this on how to prepare for the upcoming semester. I don't remember what it was called, but how to prepare through the summer. Email me and I'll give you the link, and I actually cover that in detail. All right, so easy, medium, or hard. And then how do we even, like, where do we even go with this? Well, how about instead of figuring out what it is that we have to do, start with the reactant, start with product, nah, screw all that. We are going to take a step back and ask the two important questions, get your brain unstuck, snap out of it, and figure out your next steps. So question one, what is the same? I have 4 carbons, I have 4 carbons, I have a bromine, I have a bromine. So it's the carbons and the bromine, the number of carbons and the bromine. But what is different in this case is that the bromine moved 1, 2, 3, 4. 1, 2, 3, 4. So the bromine seems to have moved from carbon 2 to carbon 4. Do I need to find a way to move that bromine 2 positions over? Is that the issue we're currently faced with? That's a trick question. And the answer is no. Do not be afraid to flip and turn and spin your molecules. If bromine is on carbon 2 and this molecule is 4 carbons, I'm just going to number it this way. And now I have to figure out how to move bromine from carbon 2 to carbon 1. I just have to move it 1 position over. What reaction do you know that will move bromine 1 position, that will move any group 1 position? And the answer is, I have no idea. I don't know how to move a functional group with 1 reaction, but I do know the pattern. To move a functional group, you're going to do a series of addition and elimination, or rather eliminations and additions, depending on which one you're presented with. Elimination and addition as many times as you need. First, we get rid of the functional group, or in this case, the leaving group or substituent. Then we add it back in the position that we want. Knowing this, knowing that my first step is to get rid of the group, it's a very easy first step. If I get rid of bromine, I want to create a pi bond, but I want to make sure the pi bond winds up in the direction between carbons 1 and 2. This is carbons 1 and 2, and I totally missed on that pi bond there. If I get the bromine between carbon 1 and 2, then all I have to do is add a different bromine. Did I say bromine? If I get the pi bond between 1 and 2, Then I add a different bromine. The fact that it's bromine means nothing. It's just something that I add to carbon number 1. Now that I have my intermediates, what am I looking at? The first one is an E2 reaction. The second one is an alkene addition reaction. So the substitution elimination chapter and the alkene chapter. To get rid of it in the direction of the less substituted side towards the primary carbon, this is going to be a Hofmann elimination. So this is the exception to Zaitsev's rule, where I want to make sure I use a big bulky base like tert butoxide in its conjugate acid tert butanol. I want to add some heat. That will give me the less substituted, less busy pi bond forming. And then I want to do an anti-Markovnikov halogenation reaction, which means I have to go with a radical route. So some students learn this in the alkene chapter, but this is really under radicals, which sometimes shows up in a different chapter. I'll put alkene above it like that. And the radical reaction specifically is using HBr and peroxides. I'll just put perox for peroxides like CH3, OOCH3, or anything similar. That will give me an anti-Markovnikov addition, and there's my final product. So again, what did I accomplish here? I moved the functional group. And so if you're given something and you need it somewhere else, just addition, elimination, as much as you need. It doesn't even have to be the same functional group because I can do that with anything. So for example, if I have a molecule like this, and let me know in the comments if you think this is easy, medium, or hard, where I have a bromine right there, and somehow, some way, I want to come up with a product that has a chlorine right there. Or, you know what, let's make it even more difficult, an alcohol. What do you think? Easy, medium, or hard? And where would you begin? Question, can you quickly explain the basics of anti-Markovnikov? I don't fully grasp it. I know it's basic. So first of all, never, ever, ever apologize for asking a question. This is what I think was my downfall the first time I took organic chemistry, because I asked what I thought was a silly question, but I didn't understand. And if I don't understand this, I'm not going to understand that. My professor made me feel stupid. My professor made me feel insignificant. Like I felt belittled. And I didn't go back to office hours because I didn't feel like I was respected for my questions. And then I wound up failing because if I can't have questions, how am I supposed to learn? And so this is not just for now. This is for everyone. Never, ever be afraid to ask. That is how you learn. I'm trying to remember that when my son asks, what, why, a million times a day. He's 3, but he's learning. Okay, so to answer your question, Markovnikov's rule is about when you have an alkene reaction. Let me see if I have some room here. No, I'll just put it down here. So when you have an alkene reaction and it's an asymmetrical alkene, you can add a substituent to 2 different positions. If I add it to the more substituted carbon versus the less substituted carbon, this is considered the Markovnikov product, and this is considered the anti-Markovnikov product. And it has to do with the substitution, the degree of substitution of the thing that you're adding, the nucleophile, in relation to the starting alkene. Now, this right here is how I learned it, how it was taught to me, and it made no sense. The idea with Markovnikov's rule is that if you want to form a product, the more stable the intermediate, the faster that will form. And so what is happening here is if I'm reacting with HX, then X adds to one side, H adds to the other side. So it's not about this. It's about the hydrogen. When I first attack right there, what happens is I get an intermediate that could look like this with a carbocation here, or an intermediate that looks like this with a carbocation here. And this is what you're looking at. Because this right here is a secondary carbocation compared to a primary carbocation, the secondary carbocation is more stable. Therefore, it is more likely to form. And because it's more stable and more likely to form, the nucleophile winds up attacking here and winding up at the more substituted carbon. But it has everything to do with forming a stable carbocation intermediate. Now, if the reaction does not have a carbocation intermediate at all, for example, the radical, then we have to look at something else. So Mira, that is a very good question. Let me know if that makes sense. Let me know if that is clear. And I actually have a video that goes into it in detail with the mechanism and more. So make sure to look for that. Excuse me. Make sure to look for that. And that way you will be crystal clear on it. No, not at all. This will stay on YouTube until YouTube decides to be done hosting my videos. All right, so let's take a look at the problem in question. Even though things seem different, professors love giving you rings to scare you. There's nothing about the ring that makes this harder except for how it looks. The substituent seems to change. It turns into an alcohol, yada, yada. The approach is exactly the same. Let me show you how easy this can be. Question number 1, what is the same? All the carbon atoms. Question number 2, what is different? And in this case, what's different is that a bromine turns into an alcohol on a completely different carbon. The fact that it turns into an alcohol on a completely different carbon means that I have to move the functional group. And even though that functional group happens to change from a bromine, which is not a functional group, it's a substituent, but we'll call it a functional group. Even though it happens to change from a bromine to an alcohol, if I do the pattern of move the group, then it will fall into place. If I have a group that I want to move, the first thing I do is elimination. I want to eliminate towards this direction because I ultimately need it to be over here. So let's find a way to do that elimination. And come up with something that looks like this right here with a pi bond. That looks like a drunk pi bond. Let's try that again. There we go. Now that I have the pi bond, if I want something here, I can't just go from the pi bond there. I need to do an addition, elimination, then addition. When I do this next addition, I want to make sure that it goes in the direction that I want this thing to move. So I'm going to do an addition with, I can do anything. I can do an alcohol. I can do a halogen. Let's go ahead and do a different halogen just to show you it doesn't matter. I could have just as easily done a bromine or an alcohol. And then I will eliminate it again because it still has to move one more position over. So I'll eliminate it again down here. And now I'm good to go for my final product. Look at that. Elimination, addition, elimination, addition, and all I have to do is fill in my intermediate. So let me know if this feels so much easier than if you just looked at this and went, oh crap, what do I do here? Well, what are my reagents? Let's go ahead and fill that in. First, let me give you the reactions. The first one is an elimination. It's another E2 Hoffman because I'm going, actually, it's not a Hoffman because I'm going to the more substituted. So just a regular E2 reaction. The next one is an alkene addition reaction to turn the alkene into a halogen. The next one is another elimination. This one is also a regular E2 because I'm not looking for a Hoffman. And then I have another alkene addition reaction, this time an anti-Markovnikov. The first one was Markovnikov. The second one is anti-Markovnikov. So let's go through and fill in the reagents. Bromine to alkene. Anything will do, so I like to go with a small, strong base, no side reactions. How about NaOCH3, which is NaOMe, it's a methoxide. In MEOH or CH3OH, add some heat, guarantee the E2 reaction. Once I have the alkene and I want the halogen, this is just a straight up HCl in something like CCl4, inert. I want to eliminate again. I can use the same thing or I can use something else. It doesn't matter. NaOH, H2O, and heat. On paper, it doesn't matter how expensive your chemicals are because you just have to show you know how to do this. In lab, you go for the cheaper one or the one that's more effective, but this is pen and paper chemistry. Once I have that new pi bond, now I want to make sure I get that anti-Markovnikov alcohol addition, which is going to be hydroboration. I will use BH3 in THF for step 1. Step 2 will be NaOH and H2O2. So Mira, I think it was your question earlier. Because this does not have a carbocation intermediate, we don't have to worry about the carbocation stability. Instead, if you watch my mechanism video, you'll see the BH3 has a very unique way of just grabbing all the alkenes, and that's why we get anti-Markovnikov in this situation. And there we go. So yes, same kind of reaction, even though it looks scarier, all it was this with a couple more steps. We're not going to do submissions right now. Esther, email me. Excellent. And you are very, very welcome. You're very welcome. So that is one pattern that I really like. Let me show you another pattern. This next one is critical for synthesis because even if you know how to move the functional group, if you have nothing on your molecule, what exactly are you going to move? So let's say you're given this molecule right here, and you're asked to come up with something that looks like this. What do you think? Easy, medium, or hard? And where do we go? We don't want to start with reactions. We want to start with the two questions. Now, if you're an Orgo 1, you haven't learned this yet, just pretend that this is something like a bromine over here, because that you should know how to do. Question number 1, what is the same? And question number 2, what is different? Well, what is the same in this case is all the carbon. And what is different is that I have nothing on my reactant, and somehow it's going to a carboxylic acid. So this is the pattern that I call the something from nothing, and this is a very common one that professors like to ask. Something from nothing means I have no functional group, no substituents, nothing that I can move or eliminate or change, and have to turn it into something. So the way I'm going to address that is very simple: radical halogenation. If I take my starting molecule and I put it through a radical reaction, then I will get something on the molecule. If you have a more substituted carbon on there, always go with bromine and peroxides. That will give you a bromine on the most substituted carbon, and then you can do whatever you want with it. So if I have bromine here, I no longer have to worry about this. Now I have a new question. How do I go from bromine at the most substituted position to a carboxylic acid at the least substituted position? Or I probably should have done like an ester or something just to show you that it's that easy, even though it looks scary. I don't know how to do that because the functional group needs to be on this carbon. So the first thing I'm going to do is move the functional group, move the position of reactivity. We're going to run out of room. So let's do this right here. Let's not lock ourselves into a corner. And then I'll put this on my clipboard so I don't have to keep redrawing it. Okay, so I have my bromine. I turn it into a pi bond in the direction of where I want my functional group to go. Because I know I want an alcohol, because I know I want a carboxylic acid, I know that if I put an alcohol, I can oxidize it, which means I'll put an OH over here, and then it's just one hop, skip, and a jump away to the carboxylic acid. If you haven't learned this, then just pretend it's a bromine, and then it's just another reaction that you do know. All right, let's go ahead and fill in the reagents. What do we have here? The first one is a radical reaction. The second one is an E2 reaction, specifically the Hoffman in this case. Here we have an anti-Markovnikov alcohol addition to an alkene. And here we have an oxidation reaction, which also comes up in your carboxylic acid chapter. Let's fill it in. Br2, peroxides. That will give me my something from nothing. This is the key step. Then I will do tert butoxide. Let's do it in a different way so you're not scared when you see it on your exam. KOTB in HOTB and heat. Potassium oxide tert butyl. That's all this is. It's just written backwards, but some reason students get confused by this. Potassium tert butoxide, that's all it is, just the big bulky base. We have the alkene. We're going to do an antimarkovnikov alcohol. So I'm going to put BH3 ... because we already saw this reaction. And then oxidation all the way to a carboxylic acid. I can use any oxidizing reagent. Let's go with KMnO4. That's step 1. Step 2, I do have to add some acid because this will give me a carboxylate, an O-. And then we just put the H+ to reprotonate it. And there we go. Pattern number 2. What do you think of this one? All right, so questions about individual reactions, given the time, I won't be able to go into them. But if you email me, I will be happy to link you to any videos or resources that I have on it, because in your case, I do have a video on the mechanism. And I actually have a question like this on, oh, I almost forgot to talk about it. Okay, the organic chemistry pre-finals assessment. I have been working on this for quite a while, at least a week. It was going to be a small assessment. Then it turned into about 60-ish questions that test you on everything in Organic Chemistry 1 in order. And the idea is, if you know you have to study everything for your Orgo 1 final, or worse, your Orgo 2 final has Orgo 1 concepts in it, and you don't know where to start, you don't know which reactions to focus on, what you do is you take this assessment as an exam, closed book under realistic testing conditions. You see how you do, and then you fill out the table that lets you know which topics you're strong on, which topics you're weak on, and what to study. So the complete assessment is something that you can purchase on my website. However, I have a free sample version of it. So I pulled out 15 questions that still give you a good representation of the different topics that you have to know in organic chemistry. And you can have that for free. So all you have to do is put final in the comments, and I will send you a link to sign up. Download it, take the assessment, see how you do. And of course, if you want the full assessment, I'd love for you to sign up for the entire thing, because it is a beast of an exam. I'm very excited with how it turned out. I'm very proud of it. And so I'd love for you to grab it. Also put live notes in the comments for a copy of today's session notes. That way you don't have to worry about remembering everything. I took the notes for you, and you can just follow along. All right, here's the problem. I wrote so many problems in my notes, but there is no way we can go through. Let's do another pattern. So starting with, and I'm not going to tell you which one this is. I'm just going to show you, because I want to see if you can come up with it. Starting with something like this, somehow, some way, show how you would synthesize a molecule that looks like this. What do you think? Easy, medium, or hard? And this is an Orgo 2 problem. So if you're an Orgo 1, just ignore this. And how would you even begin? I see hard. Challenge for you. What if I can show you that this is a very, very, very easy question? Here is the pattern. Anytime you see a molecule that seems to have grown, carbons got added. Aha, I like it. If the molecule seems to have grown and carbons got added, and there's an alcohol or something that looks like it came from an alcohol, here is what you want to recognize. Adding carbons to a chain via Grignard will form an alcohol if you attack a carbonyl. And so the carbon that is holding the alcohol, that carbon right there, would have come from a carbonyl, and then anything that was added would have been a Grignard. So that right there would have been one Grignard. We'll call that MGX right there. And that right there would have been the other Grignard. Now, in this case, Because I added two groups that are equivalent, the question you have to ask yourself is, which molecule can I react twice with a Grignard? That would be an ester or an acid halide. Or I could have done this a little bit differently. And let me show you an easier one where I can say, you know what? No, this was my starting molecule. Well, you know what? It wouldn't work because I'm starting with this. No, we have to go with the other option because of the 4 carbons. So we have to go with this one. So question number 1, let's not forget how we start this. What is the same? And question number 2, what is different? What is the same is this carbon chain that I'm going to draw in green. I have 4 carbons. And what is different is that I am adding what I will draw here in light blue, 2 ethyl groups. So I have plus 2 carbon chains. So I add them twice. But having recognized that it has to come from a Grignard attacking a carbonyl, all I have to do is turn this into a carbonyl, and then I'm good to go. And I specifically said it has to be an ester or something else that can get attacked twice, an ester and a hydride and acid halide. So I'm going to go with an ester because that's the easiest one. How do I turn? Well, actually, let's work backwards. So I know that this came from the ester, which would have looked like this, and I can add anything to it. So I'll put an OCH3. Well, how do I turn that into the ester? I have no idea. But I do know that the ester would have come from a carboxylic acid. And so I can work one step back and say this was a carboxylic acid. New question. How do I go from the alkyl halide to the carboxylic acid? I have no idea. But I do know that I can make a carboxylic acid from a primary alcohol. So I will work one step back and get the alcohol. Can I go from the alkyl halide to the primary alcohol? Yes, I can, and we've already seen that. So let's now fill them in. Chapters in question. This is an SN2 reaction, so your SNE chapter. This is an oxidation reaction, so whatever chapter covers redox. This one right here is a carboxylic acid derivative. So that would be a carboxylic acid derivatives chapter. And this one here is Grignards, which for some students show up in the alcohol chapter, but sometimes it shows up in a different one. Let's fill in the reagents. Bromine to alcohol, we've already seen SN2 reaction. Let's go with NaOH in a polar aprotic solvent like DMSO. We'll oxidize it using Na2Cr2O7. We haven't done this one yet. Notice so many oxygens, that's oxidation. To the ester, we're simply going to react it in the alcohol version of whatever OR group I have there. So CH3OH with an acid catalyst. And then we add in the Grignard, which is just this thing in excess, and it'll do the double reaction automatically. So that will be my ethyl MgBr as step 1. And step 2, I want to add in some water to protonate the O- because this will get deprotonated in the process. And that is it. The Grignard pattern, which looks like a mess, but is it that much easier when you know what to look out for? Hello, bells and whistles. Better late than never. So you have some homework tonight. Where can I find the problems that you first gave us where we ended with a ketone and a methyl group? Where we ended with a ketone. Where did we end with a ketone and a methyl group? Are you saying that the problem that I proposed this could have come from? Let me show you really quick if that's what you were asking. If I have something that looks like this, and I added 1, 2, and 1, 2. Is that what I did? With an OH. This, if I was given a different starting molecule, could have come from a Grignard right there with an MgX. And so the starting molecule for this would be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, reacting with a 3-carbon Grignard. That's 2 carbons. Let's try that again. 1, 2, 3. MgCl. Step 1. Step 2. H2O. Did I put the right number of carbons here? Yes, I did. Okay. Let me know if this is what you are asking. And if yes, if I did not limit you to just 4 carbons for the starting molecule, this would be the reaction in question. For a copy of tonight's session notes, just put live notes in the comments. For the sample pre-finals assessment, put final in the comments, and I will give you the link to grab that as well.